So this video here is for power functions, and you may ask, well, what is a power function? The simplest power function is the square root function. And a power function, the reason why it's called power function is because you can write it as a power. X to the 1/2 power is equal to the square root of x, and that's why it's called a power function. Now, we've done, so far in this class, we've done linear, which is just a line, and it looks like something like that. We've also done exponential, and the exponential's got this curve to it, exponential, and it looks like this, right? It grows. We've done the quadratic, which is a U, it's a parabola, and gravity plays a big part. And all three of these have, well, the first two for sure have significant impact in your everyday life. The quadratic is probably not necessarily, I mean, it's all about gravity and stuff, but it's probably not going to be used a lot. But the linear and the exponential you should use in your everyday life for sure. Now, the next function that we're going to deal with is the power function. And with the power function, it's, if you're dealing with a situation such as like a growth of a tree grows initially when it first comes out, it grows quite quickly, and it grows really quickly, and then it starts to slow down in its growth because as it's getting bigger, it takes more to maintain the tree that it is itself. And so what you'll see, if this is the height of a tree and this is time, you would see this tree sprout up. Once it comes up out of the ground, it's going to shoot up, right? It's going to grow real fast, and then eventually it takes so much to maintain the tree that it grows, but it grows quite slowly. All right, so it's faster at the beginning, and then it slows down over time, but it continues to grow. Just it takes a lot for it to grow, before it dies at the end. But so it grows quickly at the beginning and then slows down, but still continues to grow. And it's because the tree, that keeps on getting wider and wider and wider, and you get all those rings in the circle of the tree, and it takes a lot to add on to it. So this is a power function right here, and its format is a x minus h plus k. Now it's a square root there. Now this should look familiar. This right here looks very similar to the vertex form of the quadratic in x minus h squared plus k. So just like the vertex form, which was quite easy to do, to graph and to solve, so is the power function. The power function is really easy to graph, and it's really easy to solve, assuming that you understand that, of course, that it is the power function. And so what this video is all about, you're going to be able to graph a power function. That's one thing, and then you're also going to be able to solve a power function. And that's our two goals here for this video. So to graph it, step one is to find the locator point. So in a quadratic, the locator point is a vertex. The locator point is the significant point. Okay, so when we do this, it is the most significant point. So in a generic graph, it starts off at 0, 0, and then you graph it. And so we got to find that locator point, and that's going to tell us where to begin. Step two, we're going to create a new set of axes. Create new axis when we go to graph this. And then step three, any reflections. If there's a reflection, then we have to flip it or whatever. So those are, and then of course step four is to just simply graph. You could plot a couple of points, but simply graph would be fine here. We're just going to sketch the graph of these. Okay, so that's our goal here. Let's go ahead and get to an example. Y equals, actually let's put it on a grid. Okay, so here's our example. Y equals 2, and there's a square root of x minus 3 plus 4. So the locator point is going to be 3, 4. Just like in the vertex form of a quadratic, it's what makes it 0 here. So 3 minus 3 is 0, so that's what that is. And then, of course, you constant at the end. So 3, 4 is your locator point. So the locator point in the generic one is here 0, 0. But now we're going to put it at 3, 4. So let's erase that mark. And so 3, 4. So 1, 2, 3, and 4. and I said to create a new axis. So we're going to actually draw a dotted line here. Just dotted lines. So it's like as if we have this axis here, but now it's been shifted. And so we've got our locator point. And now the reflection part of it, if there was a negative out in front, it would reflect, but there's no negative there. If there's a negative in front of the x, it would reflect, but there's no negative there. So now we just simply graph it. We go and sketch it. So let's go ahead and sketch the locator. And we could plot more points on this, but we're just going to go ahead and do this. If I wanted to plot a point, which you could, if I wanted to put in, say, 4, so I've got 3, 4. If I wanted to just go 1 away at 4, that would give me the value of 6. So if you could see at 4, it is at 6. So it's pretty close in my graph there. And it's always that number there if you're going 1 away, assuming that this is just linear there. Okay, so that's the first one. All right, let's do another one. Y equals, let's go 5 square root x plus 1 minus 3. Now the new locator point here is just like the vertex form. It's at -1, -3. There's no reflection because there's no negative sign out in front, and there's no negative sign in front of that x. And so -1, -3. So the next point would be at 0, and it would be 5 away, so that'd be at 2. So -1, -3. So -1, -3, 1, 2, 3. And at 0, it goes to 2. So we've got the new axis going through our locator point. And we're going to go ahead and graph it, like so. And that's your power function. I'm going to show you one with a reflection. And this is probably the only reflection that we'll do in here, is if I have -2 out in front, x, let's go x minus 1 plus 4. Okay, now and it will make sense that there's a reflection here. If I look at the locator point, it's at 1, 4, so it's at 1, 4. Here's my new axis. And 1 away from 1 is 0. Excuse me, is positive 2. Well, 0 is 1 away also, but you can't square root the negative, so I can't put in 0 here. If I put in 0, I'd get 0 minus 1, which is square root of -1. That doesn't work, so we only have 1/2 of the graph there. And so anyhow, if I do this, if I plug in 1, I've got 4. And if I were to go to the next number, which would be 2, I would get -2, and I'd get 2 minus 1 plus 4. And so it would end up being at 2, because this is 1, and so -2 plus 4 is 2. And once again, it's just 2 lower than what we had. And so now you've just got yourself a nice graph like this. Now the domain of these graphs, the domain is not all real numbers. In a quadratic, an exponential, and a linear, they've all been all real numbers. Now the domain is limited, meaning that there's only part of a graph. So when we talk about this graph, it is just the positive values of x. X is greater than or equal to 0. No negative, because you can't square root a negative number. You know, -1, that's not real. It's an imaginary number. And so it's not real, so we can't do that. We can only square root positives. So like square root of 1 we can get, but square root of -1 does not work. So if you see error, that means it's not in the domain. That would occur when you have that. So how do you find the domain? Well, if I have x minus 5, then I would take this, and I can solve this inequality to find out when it's bigger than 0. If I solve it, I have 5 to both sides, x is greater than or equal to 5, and that would be your domain. So if this had been my graph, it would be shifted over 1, 2, 3, 4, 5, and I could not plug in, say, 4 in this problem, because 4 minus 5 is -1, and that's not cool. So that would be not cool, not part of the domain. But 6 is, and 7 is, and 8 is, all those that are bigger than 5. All right, on to goal number 2, which is to solve. That's our next thing. To solve these are really quite easy. It's just like the completing the square ones. You're isolating. It's all about isolation. Isolate the radical. And then once we do that, square both sides. We are undoing the radical by squaring it. So an example of this would be 3 square root of x minus 1, say plus 2, equals, let's go 14. Now, to isolate this radical, I've got to isolate this. So I've got to get rid of the plus 2. That means I'm going to subtract it over. And if you're listening to this video, when you get done watching this video, come tell me, your favorite place to go on vacation. And then the next thing, after you've isolated the radical, or almost isolated the radical, divide by 3. And so this cancels, so that gives you square root of x minus 1. Now the radical is all by itself. Once we've isolated the radical, we can undo it. So the opposite of a square is, opposite of square root is squaring. So we can square both sides. It's the inverse here. And so that's going to make 16 here. And the square and the square root cancel each other out. And then of course the last step is to solve for x. So 17 is my answer. Okay, so we're isolating the radical. So let's do another one. Let's go negative 5 x minus, let's go x plus 2. Let's go minus 3 equals negative 33. I think this is going to be okay. If I add the 3 across, I'm isolating the radical. So now I have equal to negative 30. And then still isolating the radical, divide by the negative 5. And so you get square root of x plus 2 equals 6. You square both sides. We've isolated, we square. And so that gives us 36 on the right side. And the radical and the square cancel each other out. So that's going to give us x plus 2. And if you solve this, you get minus the 2 across, you get 34. So 34 is my answer. Now, the one thing about a power function, you have the chance for an extraneous solution. If I go back to and plug in 34, you'll get the correct answer. Extraneous means you did nothing wrong, yet it creates a false solution. And the way that we solve this by squaring both sides can create a wrong answer. Because if you graph this, and our graph went like this, negative 33, it will hit. But if I had done a problem that was up here, we could get an answer, but it would only hit if we had the other half of the graph, but we don't have the other half of the graph. So we'll give you an example of one that's an extraneous, a very simple one. Square root of x equals, let's say square root of x plus 2 equals 1. And if I subtract the 2 across, I've done nothing wrong algebraically, and I square both sides, negative number squared is positive, so we get x equals 1. Everything seems fine. However, if I were to go back and put 1 in for x, square root of 1 is 1, plus 2 equals 1. Nope. This would be no solution. And I want to show you on the graph why this would be. Square root of x plus 2 would be, up 2. This was square root of x plus 2. And we want to know when it equals the equation 1. Because remember it said equals 1. When does it equal 1? Well, does it ever hit this? And the answer is no. It'd be no solution. So that's one thing that you could also get on that, and that's called an extraneous solution. So extraneous. Because we solved it totally fine, yet it created a false solution. I hope this is helpful.